Good morning, good afternoon, good evening, wherever you are. This is presentation number 3 of the Marine Surveying International Fest 3rd edition. I'm delighted to welcome joining us from Italy, Luca Olivari. Luca is a naval architect and one of the foremost European experts in composites. So I'm going to leave Luca to give a self-introduction to himself. Delighted. Thank you very much, Luca, for joining us today, and very much looking forward to hearing your presentation. Over to you.
Okay. Good morning. I'm Luca Olivari. I'm working in Italy. I spent also some time working in England for actually Gurit, and at the time was SP system, and I made structural engineering with composite material for every kind of project, not only boat but also train and ship funnel and so on. But mainly my job is now about Powerboat. So I will start to speak about the experience I made in the past about the slamming phenomenon. That is common, of course, in high-speed powerboat, but also in the new light and flat sailing boat. When I approached this phenomenon, it was that I was in charge to design a class 1 a class 1 powerboat designed by Michael Peters. At the time, the winning boat was made in aluminum with a structure that you can see in this picture, and it was the early 90s, and it was the state of the art was the aluminum. When I was in charge to design a composite structure for this type of boat, and it was very difficult to know what are the pressure acting on the bottom of this type of boat that are running at speed that are higher than 160 miles per hour. So I went to a existing boat that is shown in the picture, and I measured the deformation of a bottom of a hull in aluminum, and from with this permanent deformation, I was able to re-engineering the pressure that was acting on the bottom of the hull, and there was very high pressure, so high that it was not possible to imagine that we have acceleration for this pressure higher than the 16 G acceleration. So this at the end I developed the concept that this so high acceleration that was fatal for the driver was dissipated in the structure, and it was acting on the bottom of the hull for very fast short period of time, so millisecond. In this picture you can see the difference between the aluminum structure and the first of this boat made completely in pre-preg UD carbon fiber and Kevlar and carbon bottom reinforcement, high thickness core. The bottom was a 60 millimeter, 200 kilo density thickness, and the structure were made in female molds, glued together, and everything was glued to the hull without any more taping of fiber laid by hand. This is the first boat that I designed and built, and was built by Tenkara. That was the the boat that started, was born for il Moro di Venezia America's Cup syndicate in Italy, and this boat at the first year that was launched, they won the world championship, and here are the pressure acting on the bottom of the hull in kilonewton. So you can see that in the engine area we have something like 70 tons per square meter of pressure. So really, really very high pressure. From this experience, I developed a lot of data about the behavior of a bottom in a slamming condition. There was also DNV research about this, and they are shown that the slamming is acting in a really fast time, that you can see that is recorded in a millisecond, and so on. And they did also they instrumented a part of a boat and dropping it in the water to understand better the phenomenon. But at the end of this, I was and after the experience of several racing boats, I was able to define some basic slamming composite concept. One of these is the structural grid. So the pressure on the bottom is related to the size of the panel. So if I reduce the size of the panel, the specific pressure is increasing, and if I have a relatively big panels, my specific pressure is reducing. This means that a bigger panel is able to absorb more energy during the slamming. At the same time, a bigger panel presents the problem to be enough stiff and resistant for the applied pressure in any case. So one of the key concept is that the laminates has to be strong, but at the same time very simple, and to have a good fatigue resistance. They need to be aligned, the fiber need to be aligned on the right orientation, and this means that I am increasing the short side of a panel with UD fiber on the longitudinal orientation of a boat. So you can see my this is a typical very simple structure, and we will spoke about this later. I have only transversal frame, and the panel are relatively big, and so my fiber are mainly oriented on this way, so longitudinal. Another critical aspect, let's say the most critical aspect, is the core. At the time that I was designing the first high-speed powerboat, the class OP1 class, Diab was testing a new foam that was tested for the mine hunter. They wanted to develop a foam to build a mine hunter in a sandwich, and to be sure that the core was at the right resistance. They made sample really large panel submerged in the water, and they exploded the mine close to this panel and tested if the elasticity of a core was enough. So they developed a core that was at the time 200 kilo density, and with very, very high shear elongation, up to 50% of the shear resistance. So it was a strong but very, very flexible foam. And this foam was used for the first time also in this racing boat. About the structure, there is another detail that is important: to have a good link between the hull and the structure, and this was shown also in the first picture. All the structures are bonded with a structural adhesive that is capable to transfer much better the loads from the hull to the internal strata. In this case, the structural adhesive is methyl methacrylate, and that is also able to support a considerable thickness of a glue, and it's work very well. At the time, most of the boats that I am designing are completely have the structure completely glued. So after this, I will speak briefly about what's happening when for the slamming of a boat when it's break. And these are two pictures that showing what's happened. This is the bottom of a big sailing boat, not a power boat, 35 meter length, and it's possible to see that these are the stringer at the sides, and this is the center of the panel, and the panel has the lamination and rupture in close to the side and the corner of the panel. This is a picture that is shown that they cutted out some piece of internal skin to see what was inside the core, what happened inside the core. Then on this area where is the yellow line. These are the area that sound delaminated, and after cutting the core, it was possible to see that the core was a contour core, cutted contour core, and in some part it was really completely exploded. This is the analysis from the out of bottom of a boat in the same position, and it is possible to see on the dotted line the structure, and it's possible to see what are the delaminated area with delamination of the skin, also up to core damage. Everything is close to the corner of the panel. This means that the main objective is to have a panel, a structure that is capable to absorb energy fast and to dissipate it in all the structure, not only in this panel. So the flexibility, relatively flexibility, is vital to solve this problem. These are the test made on part of sample of the same panel that what was found broken, and you can see very well how the cut inside the core is influencing the breaking mode of a core. This is a plain sheet core, and you can see that the skin is collapsing, but the sheet is let's say is not broken, and this is a double cut, and you see that I have a shear breaking, and this is a triple cut, and I have at the same load with much more breakage by shear of a core. This means that to maintain the properties of a core, so to maintain the elasticity and the elongation of a core, is very important to have plain sheet panels made by plain sheet material. The cut, double cut, triple cut, are increasing the stiffness at all if they are very well filled with the adhesive, but at the same time, increasing the stiffness, they lose the capacity to absorb the instant energy of slamming, so they lose also fatigue resistance. So this is, it was only to show the main characteristic of a slamming phenomenon. After this, after defining the structural grid, it was possible to so now I go back, and now after this I want to speak about another boat that is from last year, that was developed and built here in Italy, that also beat the speed record at the Monaco electric boat challenge last year. This was Anvera, eLab, and they ran the mile in 74.49 km/h. Probably the boat can be also do better, but so this boat is compared to the other powerboat is relatively simple to be built. The target for an electric boat is to be as light as possible, because the critical aspect is that the weight of batteries that she has to take with on board. This boat is 9 meters long, very, very slim hull, and it takes 800 kilos battery inside. The weight of the engine is not so much as I remember well, is let's say something less than 50 kilos, and the overall weight of a composite structure, that so I mean the finished boat, hull, structure, and deck all together is a weight of 320 kilos, and designed to run at speed over the 50 knots. I used a software to make the basic analysis of and optimize the laminates of the bottom, of the sides, and of the deck. Here is possible to see a typical panel of a bottom, and the reserve factor on all the panel. The blue is where I have a lower reserve factor, and here where I have green and light blue, I have a higher safety factor. That means that at the sides and the corner of a panel, I have a maximum stresses, especially in shear. So you can see that the reserve factor is 2.35 at the corner, so quite a good reserve factor in any case, and it is increased at a higher factor at the center of the panel. The same panel, you can see the deformation, and at the center of this panel, that is 1.2 per 1.2 meter length, I have 9, close to 10 millimeter deformation. Of course, the panel is made by UD carbon fiber skin, very thin, you will see, and a thick, heavy core that was recently developed by Diab, but that is called HM, and this is the HM 100 kilo density. This is the analysis through the shear of the typical panel of the bottom, and at the panel sides we can see that this is the core, and I have where I have the 2.5 safety factor, and these are the skin the outer skin and the inner skin with UD carbon fiber material layered at plus minus 45, and I will explain why. And you see that the the skins are much higher safety factor compared to the core. But if I go at the center of the panel, the ratios is inversed. I have a very, very high safety factor for the panel, for the core, and the minimum safety factor for the skin. So this means that what I did, for instance, in the class 1, also having 200 kilo density core and also having 60 millimeter thickness of a core for panel that was close to 700 per 700 millimeter size, so relatively small. I needed to put some more reinforcement under the transversal frame where the shear strength is concentrated. So I put it under the frames omega carbon fiber omega reinforced area. But this was not the case of this boat that is much lighter and also much slower. And so the bottom of the hull was simply made by 2 layers or of biax, carbon fiber biax at plus minus 45 degrees. So very thin skin, 0.9 millimeter, and the bottom chorus was made by the HM100, 30 millimeter thickness in green, and Nomex was the size was made in Nomex, 48 density and 20 millimeter thickness, as is possible to see in the section. So very simple construction. I made also a simulation with a final element analysis to check better the behavior of the structure, and these are the result. This is a typical section of a boat with the transversal frame that is made in carbon fiber, built in a female mold, and glued inside the boat through a flange that is shown here. So you can see that these are the deformation. So you can see the maximum deformation at the center of the panel, and it's possible to see that the frame is relatively stiff, and so this is the behavior of the boat. After on this, I made the analysis of reserve factor that is calculated with a quadratic criterion that usually is Tsai-Vu or PUC, and this is a criterion that is very conservative. That it shows the first ply failure of one of a layer, and it's evaluated not on the fiber failure but on the matrix failure. That means that at the first damage on a laminate is the first area damage in a laminate is the metric resin that is between the layer. So if you go to a laboratory where is made the testing of a composite material, you can, before having the maximum resistance breaking load, you can hear noises that are made by the resin in between the layers that is start to micro cracking. So this is the critical failure first layer modified POC criterion. And I put one is there is one layer that is starting breaking, and now the scale is at 0.5, and you can see that all the structure is very safe. I have concentration on the corner. I have concentration where I put the boundary in boundary condition for the model, but mainly I have all the structure that is acting in a good safety factor. The applied load was of let me see if I remember. It was 45 kilonewton. That is means 4,500 kilos for a square meter. The load is not so high then to determine the load is the weight of a boat is one of principal aspect, and so 45 kilonewton for a boat running at more than 50 knots is relatively a light load. After I have a result that of one of the critical parts of a behavior of the adhesive that is between the frame and the bottom, and this is a large picture that you can see where it was put the glue. The model is made by a shell element, and the glue is made by solid element that is possible to to see it in detail here, and so I can analyze the shear and the tensile loads acting on the glue, and this is these are the stresses in shear on the glue. You can see 3.3 MPa at compression maximum, and 1.5 MPa in tensile and shear strength. So that means that I have a very large safety factor that this was used was adhesive that has at least 11 MPa shear strength and 20 MPa tensile strength. So shear stress is minimum safety factor superior at 5. I go forward and showing a typical structure of a boat. There was mainly transversal frame, only transversal frame, and a couple of bulkhead, or everything was built separately. Something This C-section frame was built in autoclave to save more weight and have a better construction quality. And is made in a female mode in this. This is a construction sheet for the yard, and you can see that the lower part is more reinforced and so on. And these are the laminate of everything carbon fiber biaxial. This is a typical bulkhead that is also reinforced VUD tape to take better the compression of the hull. And this was made also outside, but was not glued, but was laminated at the boat directly with a vacuum bag. This is a more detailed drawing of one of the bulkhead before the cockpit of a pilot. The pilot were, this is the battery volume, and this is the engine volume. The transmission is like a surface propeller made, and yes, it's all. Some part of a bulkhead is in single skin. The central part that is a bigger panel has also a core, Nomex core reinforcement. And these are the picture of a construction of a boat. You can see the boat was built in two halves to have a better access for the construction, so to make it more easy to be built and to have a better quality of all the lie up of a layer and the core. So this is the I think the gluing under vacuum of the core. You can see that the core is in plain sheet, of course, and with small holes to let the air of lower side coming up and go out of a surface that has to be built. The Nomex was not already made. And this is the result at the end. Before the inner skin, you can see the HM 100 density panel. Of course, all the spray rail was filled to have a straight skin under the core. This is also a very, very important aspect. And also there is the the Nomex core already also glued to the outer skin and ready to be for the inner skin lamination. The two halves were put together, and the inner skin was made in one step from left to right, after making also the the junction of outer skin down. Of course, on this boat there are the core is always has the same density. In a boat with higher load, under the structure he will be put a core of higher density, like the 130 or up to the 200 if the boat is big and very fast. This is the construction of a deck, very simple deck, so very easy and light to be built. This is the core with very thin fabric, glass fabric to support the lamination of inner skin of a deck. Here is the cockpit area and one hatch and some reinforcement, but is at the minimum. On the corner I have also a stripe of foam to close the side of a Nomex core. And here is the boat when in construction, by installing the the bulkhead and all the structure inside, and it's possible to see that the bulkhead are laminated inside with a filler that is put before the lamination in vacuum. This is the part where is installed the the engine, and this is the area where are put the the batteries. You can see somewhere, yes, somewhere that is the reinforced. This is the reinforced bulkhead. They weighted everything as is possible. This is 16 kilos heavy, but also we have part with 1.46 kilo, and all the pieces were very light. This is the construction of the transversal frames in autoclave, and is the final result is this. You have a C section. This is before gluing it. We left a 5 millimeter gap for the glue, and these frames are weighing, let's say, a couple of kilos each. And this is the finishing of a boat, and also this is the tunnel where are placed the batteries, and the rules ask to make all the test, the running. They have a endurance test and a speed test. The endurance means that they have to go from Monte Carlo to Cannes, make a pit stop, recharge the battery, and go again to Monte Carlo in the minimum time possible, including also the recharging of the batteries. And this is the endurance. The speed test is a test to run 1 mile twice. I think at a medium speed that is measured on the mile. This is the boat during the speed test, and it was at the first trial. There was not so much time to optimize all the battery and engine power, but now we are confident that it's possible to reach much higher speed, close to 70 knots with this engine. The final weight of a boat, as I said, in this, so how you see it, it was 340 kilos, and for a 9-meter length of a boat. And also this was with first people, and 3 people, and it's all I want to show you. But for give you an idea, the a class 1 powerboat is the length is about 50 feet length. This boat, the composite structure is close to 2,000 kilo carbon fiber and foam. So let's say, in any case, a good weight. If you think that here the pressure are not 45 kilonewton, but 700 kilonewton. I'm looking if I have show you everything, but so to speak for the future, I'm designing actually, and one is already finished, a bigger power boats, 63 feet length for Lamborghini. And this is a fast cruising boat, full of things put on site, so this is much more difficult than on a racing boat to take the the load down, but the expected speed will be 65 knots for a 63 footer cruising boat is quite a high speed. And I am also designing a bigger one at 84 length, also powerboat, that will start the construction in these days, and the boat will be completely carbon fiber construction, with every kind of sophistication to keep the weight down and the stiffness very high. And the expected speed for this boat, that is 84 feet, so quite big, is of 75 knots. And so is a good challenge to reach the speed with this size of boat. And so all these new projects are based on the experience made in the past on the racing boat. So I think that I have finished. If you have a question, I would like to give you answer. If there is something that you are curious to know about this concept and this type of boat.
Well, the first question, it's Mike, Luca. The first question I have for you is from James, who would like to know how much it cost.
I also don't know exactly how much it cost. Fortunately, I don't have to pay it for, but the electric boat was a prototype. I think also that the builder does not know how it costs, but there is something that is also a rule that is also good for the sailing boat, that the cost of a plant inside, of interiors, very sophisticated, and interior is so high that sometimes the construction cost is not so relevant. But I think that for the 63 footer Lamborghini, the cost of a composite part is about 700 euros, 700,000 euros, and I did it right, yes. And for the 84 footer will be about 1,200,000 euros cost of a composite construction. The Lamborghini 63, I think that will be the cost. I'm not absolutely sure, but around the 4 or 5 million euros for the finished boat. Yes.
I'd like 2, please. Can I order 2?
Yes.
So I have a question from John, who says, sorry if you covered this and he missed it. How much did the machinery and the batteries weigh? What was the weight of them?
I don't know. I don't have. Wait a moment. I don't have much information about all the system of battery engine. I know only that. Let me give a look. That was designed by the company. All the electronics was designed by the company that is working close to Ferrari. So they should be very expert about the use of battery and so. I'm looking if I have some data. But I don't. Now I have a database of this thing, but frankly I don't give so much attention to. Let me see if I find something, but I opening a PDF. See, the batteries are lithium batteries, Korean lithium batteries, and let me see what are the characteristics that I don't find. No, I don't have the characteristic of the batteries. Yes, probably somewhere, but I don't find it.
Don't worry, Luca. Don't worry.
Okay.
Okay. So, any more questions?
Yes. Good morning, Luca. It was really interesting. Thank you for that. I see more and more boats with cracking due to slamming. But also on more on finilester yachts. And I was wondering the difference between the stiffness of the stringers and the flexibility of the hull cause, in my opinion, the most cracks. I also saw this green filler on this bulkhead. I think the difference between the method of gluing the stringers on the hull should be more flexible to avoid this cracks over there. What's your opinion about that?
My opinion is that so going back to to the beginning, we are actually all the designer mainly, yes, okay, and also the boater are practically trying to build composite structures that are similar to the classic material structure. So the classical structure is stringer, transversal frames, everything is made for a steel or aluminum boat. One of the weak points of a composite structure are the crossing of a structure. then in the crossing of a structure, let's say the crossing of some transversal frames with longitudinal, I have shear efforts as is possible to imagine, and these shear are transferred only by the strength of matrix of a resin and not by the fiber. And so as is possible to see here, but what I am doing also in the bigger boats, I try, if it's possible, not on in the complete boat, I try to have only transversal frame, cioè I avoid the crossing of longitudinal between this is then where I have the crossing point, I have a weaker point and also a concentration of stiffness that is not the main the best for the slamming.
Yeah, because then actually we are creating a hard spot in that area. What
yes, exactly. All the concept has to be the target of a concept is to maintain avoid the concentration of stresses in every part of a boat, from the structure, from the hull, from the corner. Everything has to be designed to spread in the best way the pressure and the effort and the loads of a boat.
Okay, well, thank you for the answer.
Sorry?
Thank you for the answer.
Okay, any more questions for Luca? Our time is just about up, Luca. You've filled your slot perfectly, and it's great to have a structural presentation. This is not the sort of thing we normally deliver enough of, I think. So I'm very, very grateful to you for joining us today, and thank you for being part of the Marine Surveying Fest.